Hi, and welcome to the Foundations course lesson 3 on the basics of statistical inference. Today we're going to look at population versus sample estimates, the meaning of statistical inference, and the central limit theorem. And this will be an easy step up towards understanding the concepts explained in lesson 4. So we're going to start with population versus sample estimates. I already alluded to this concept briefly during lesson 1 on data summary measures, when I told you that different calculations and different denotations are used for sample and population mean as well as standard deviation. So we already discussed that in the population we use the Greek letters mu and sigma to denote mean and standard deviation, whereas in the sample we use bar over x and small letter s. But why do we do that? Well, let's look at the population for a moment. With population in statistical sense and medical research, we do not refer to the global population on planet Earth, of course, but we're referring to patients with a certain disease in a certain setting. And now, let's say that all these patients that are depicted here in this graph resemble a certain study population. So we have 50% male and 50% female, and there are different colors that all represent various patient characteristics. Now let's say we take a sample out of that population. We end up with these patients. You can see that we mostly have females, 73%, and only 4 males out of 15 patients. Furthermore, we do not have any green patients, and we have a very skewed distribution because almost all of our information comes from blue females. So it's a small sample of 15 patients, and as I alluded to, almost all our information in the sample comes from blue females. So it's probably not a random sample. In other words, it is highly selective. And it would be good in this case to think of a reason why we have selected so many blue females. And what's important to realize is that we cannot infer any information about the population from this sample. And in theory, we could accept this and try to infer information about the population of blue females. But there's a problem here because we are also not sure that this selection is representative of the smaller or more selective population of blue females. What's better is to draw another sample and make sure that it's larger and random. So let's do it. Now we're going to take this sample and we're going to end up with these patients. And as you can see, 50% of our patients are male and 50% of other patients are female. And we have an equal distribution of the patient characteristics. So this is a sizable sample of 100 patients, and it's probably random because it resembles the population pretty well. I do have to note that random chance can still result in slight differences within samples, especially in smaller samples, and I have depicted a perfect sample here. And in medical research, that's almost never the case. But we can use the sample to infer information about the population. Now let's talk about the meaning of statistical inference. When we try to define it, we come up with something like the process of inferring population properties through statistical analyses performed in a study sample. So what do we mean by that? Research is about uncovering an unknown property of the study population. We cannot analyze the entire population, so we design a study, start the data collection, and that actually means building the random sample, And we evaluate those collected data by looking at potential sources of bias, because they might have led to select a sample like we have seen before. And we derive estimates of the values that we are interested in and perform hypothesis testing. And through this analysis, we infer properties from the population out of our sample. The central limit theorem is something that lets us do that. And it's eloquently described by Charles Whelan in the fabulous book Naked Statistics, Stripping the Dread from the Data, like the LeBron James of statistics, if LeBron were also a supermodel, a Harvard professor, and the winner of the Nobel Peace Prize. So you get the concept. It's a very powerful tool, but it's hard to understand what it actually means. And to understand that, we need to look at a population distribution. So let's say this is a histogram of a certain value, but it's the histogram of the distribution of that value in the population. And the mean in the population is 0 and the standard deviation is 10. Now let's say we were to take 500 samples of 250 patients measuring this value out of that population. If we would look at the distribution of the value in those samples, we would see something like this, where the mean is not 0, but it has a spread from sample to sample. Some of these samples show a mean of 1.58, and other samples show a negative value. And the standard deviation is also variable between those samples. And these are only 8 samples, but imagine that we would look at all 500 of them. And now the next step is to think that we were to plot the means of all those 500 samples in a sampling distribution of its own. This would result in a histogram like this. And what's interesting is that the mean of the sample means is 0. So it's clustered around the population mean. And this is what the central limit theorem dictates, that the mean of the sampling means equals the population mean. Now, another concept that's important to understand is that of the standard error. It's a measure of spread that we haven't discussed yet. And the standard error, formally defined, is a measure of the dispersion of sample means in the sampling distribution. But saying it more simply, it's the standard deviation of the sample means. And officially, it's calculated by sigma, the standard deviation in the population, divided by the square root of n observations. But we can approximate it by the standard deviation of the sample divided by the square root over n. And now we've looked at the population histogram, the histogram in one sample, and the histogram of the sample means. I can understand if you're getting a little confused by now, but just hold on a little longer, and I hope that things will clear up in just a second, because we're going to start to tie all these concepts together. In medical research, we work with one sample, and that sample gives us a sample mean and a sample standard deviation. But what we actually want to know is, for example, the population mean. And we're going to estimate it from our sample mean. And we can do that by using the standard error. You can interpret that as the uncertainty with which we can estimate the population mean value by the sample mean value. Formally, the standard error is defined as the standard deviation of the mean of multiple sample means. Like if we were to repeat our experiment multiple times, Of course, that's a theoretical concept called the central limit theorem. But we know if we were to look at the spread of those sample means that they tend to cluster around the real population value. So this allows us to perform statistical analysis with things like the standard error to infer properties from the population through our sample. So what sort of things can we do with the central limit theorem? For example, if we know population properties, which by the way is not often the case in medical research, we can estimate the likelihood that a sample originated from that population. And as I've explained, if we have a large enough random sample, we can draw inference about the properties of that population. Furthermore, if we have two large enough random samples, or in other words, two different groups in a study, we can estimate the likelihood that both samples come from the same population, or in other words, whether they are different. I want to end this lesson on the notion that standard errors follow the standard normal distribution, just like the z values that we've encountered before. And what that means is that we can calculate the probability of encountering certain standard errors, just like depicted in this graph. Alright, that's it for basics of statistical inference. Great job. This was actually a tough lesson, so thanks for hanging in there, and I want to say get ready for hypothesis testing and the p-value.